Hello, today we're going to be discussing projectile motion, and this is by Kelsey Heiss, Cassidy Starling, and myself, James Ray.
Projectile motion is a form of motion in which an object is thrown near the Earth's surface. It moves along a curved path under the action of gravity only. Gravity acts downward to cause a downward acceleration on the object. As you can see in this picture, as the football is kicked into the air, it forms a parabola shape. There are several factors we will discuss today concerning projectile motion. We will begin by discussing velocity, and we will then move on to forces. We will discuss two types of velocity, velocity in the x direction and velocity in the y direction, and how those compare and relate to projectile motion. We will also discuss gravity and drag force, two types of forces found in our analysis.
Velocity is broken down into components along the x and y directions. Velocity in the x direction is equal to the initial velocity, whereas velocity in the y direction is equal to mass times gravity. As shown in the picture, the velocity in the x direction remains the same throughout the ball's trajectory, whereas the velocity in the y direction points upward as the ball rises and points downward as the ball falls. Velocity in the x direction remains the same as the initial velocity, therefore the sign remains the same. Velocity in the y direction decreases as the object rises and then increases as the object falls, therefore the sign changes. As you can see in the picture, the x component of velocity remains the same throughout, whereas the velocity in the y direction decreases as the ball approaches the top of the parabola. At the top, the y velocity is 0, and then as the ball continues to fall, the y velocity continues to increase.
For our project, we decided to analyze the projectile motion of a ping pong ball being hit across a ping pong table. We used a 38 millimeter and .0027 kilogram ball. As you can see in this video, James hit the ball from the right side of the table and the ball bounced in a parabola shape.
We used Tracker in order to analyze our data from our parabola motion of our ping pong ball. As can be seen in this image, the black parabola track is actually the track of the actual ball, in which it does have drag force acting upon it, as well as the other forces that were present in the simulation. In addition, the blue track that is above is a model of what the ball would look like without outside forces acting upon it. In future slides, we will look upon and determine what forces are actually acting upon it that would relate to the difference in the tracks between the model and the actual parabola shape from our ping pong ball.
This graph shows the actual trajectory of the ball. As you can see, it's not a perfect parabola, which is most likely due to the fact that there are too few numerical values for our data points.
As you can see here, this shows the model trajectory of the ball, which exhibits how the trajectory should look. As you can see, it forms a parabola with a perfectly smooth curve, which is most likely due to there being a larger number of numerical data points.
As can be seen in the original image, the black parabola was a path of our ball. In this black parabola, it did include drag force as well as other forces that were acting upon the ball. On the other hand, however, the blue model track did not include drag force or other factors outside of the ball. A ball traveling through the air, though, will experience a backwards force due to the fact that the air pressure on the front of the ball is larger than the force at the back of the ball, and that is called drag force. And the force is larger in our instance because the force of air is pretty heavy. So, as can be seen in this model, the force of the drag force does act in the backwards direction while gravity acts down. We're neglecting lift due to the fact that no intentional spin was put on the ball whatsoever. So, therefore, lift possibly could have occurred, but it wasn't substantial enough to show the difference between our model and our original path of our ball. In order to account for the drag force, we included a model in which included the equation for drag force, which is seen here by the red model. In this model, as you can see, the model line parabola does match closer to the original parabola of our ball compared to the original model, which is the blue one. But as can be seen, there's still a large difference between the original parabola motion of our ball and the model.
This shows model drag force. In the same way as before, the parabola has a smooth curve due to there being a large number of data points.
As can be seen in this image, to our model B, we included an additional force that we noted as F. For the force, we put in 0.0399 newtons, as can be seen in the top right portion of the screen. We plug this into the equation for the y direction of negative m times g minus f. Once we plugged in this additional force, we did get a better matchup between the parabola of the blue model with the actual parabola of the black model. This, we believe, is due to the drag force that the model didn't account for compared to our actual model force. In addition, the force could also be a result of outside forces such as the air currents coming down from the vents above us, which could be a result of heat or air conditioning, as well as the air current that would be coming underneath the door. In addition, there could be another force acting upon our ball, which could be spin. We neglected spin because no intentional spin was put on our ball, which would have caused lift. So we believe that the overall force that is causing the drastic difference is the drag force, which can be accounted for, the 0.04 newtons of force that once we factor it in, that would be a roughly significant number that would match up with what our models are showing. To go a little deeper into drag force, as can be seen by the drag equation, drag equals the drag coefficient times the density of the air times the velocity squared divided by 2 times the reference area. And for our ping pong ball, the drag coefficient of a smooth sphere, which is like our ping pong ball, is actually a function of Reynolds number at very low speeds. And basically the Reynolds number is just a basic ratio between momentum to viscosity, viscosity being the air. And in this instance, we use the air viscosity as being 1.789 times 10 to the 5th kilograms per milliseconds. So the Reynolds number is around 2,700, and as a result, anytime you have a Reynolds number that is between 750 to 200,000, then the drag coefficient is approximately the constant at 0.445. For the density of air in this equation, we just use 1.225 kilograms per meters cubed, since that is the density of air at sea level at around 15 degrees Celsius. When finding the area that is referenced in this equation that relates to the ping pong ball, the area does come out to be 6.8813.
In addition, another variable of this equation is velocity. The average velocity in our results was about 2.5 meters per second squared. As a result, after we plugged in all of these different factors into our equation, we found that it comes out to be a number that is roughly right around where we factored in the value for the additional force. So therefore, the drag force, as we believe, could in fact be the difference between our first two graphs. So overall, we do believe that the drag force is the outside force that causes the difference between our two parabolas. Another possible source of error could be the tracker placement on the center of the ball. As you can see in these pictures, the more you zoom in on the ping pong ball, the blurrier it becomes. Therefore, there is no way we could be 100% accurate for every data point. This could definitely have an effect on our analysis. In future studies, we need to use a better camera that has more of a sport mode with a higher shutter speed that will allow us to get more frames per second, so we are able to zoom in more on the ball and have a clearer picture so it's not as blurry as it was in our results. In addition, our camera angle does make a huge difference, so hopefully in the future we will be able to line that up more in a 90-degree angle in order to ensure proper measurement. And last, our distance needs to be measured more accurately along the ping pong table. Now that you have learned a little bit more about the projectile motion of a ping pong ball, are there any questions?